Shall I kick off, Gary?
Yeah, let's get into it.
Yeah, fair enough. So, hi there. I'm Gordon Harling. I'm president and CEO of CMC Microsystems. So we're a 40-year-old not-for-profit, and we were originally created to provide access to Nortel's fabrication line, but they didn't want to deal with a whole lot of questions from newbies, from people who had never done a design before. So Pierre Elliott Trudeau actually gave $1 million to a fellow named Doug Colton to form CMC. And over the years, we've expanded so that we realized that people needed computer-aided design tools to design chips, and so we offer about 15 or 20 different sets of design tools, including the big three: Cadence, Synopsys, and Siemens. And I was talking to Cadence a little while ago, and I asked them what is the value of the bundle of tools that they give to us, or I should say, they sell to us, but at a deep, deep discount. And they said that the market price for these tools would be $42 million per person per year. So we have about 1,500 copies of that, and we roll it out to about 12,000 users all across Canada. So sorry, we had a bad year last year. It was 11,800, but I like saying 12,000. And that's about $60 billion worth of software from one single vendor, and we have a number of different vendors. So it's a huge benefit to Canada that we have that kind of capacity and capability. And then what we do is we carry through the from design. We can hook up a process design kit, so you can design into a specific process that can be fabricated. And then we have about 20 factories around the world where we have chips fabricated. So we can do everything in microelectronics down to 12 nanometers. We do photonics. We do micro electromechanical systems, which is a big thing in Canada. But we have other factories around the world as well. And we're one of the only people who do a cost shared service for doing superconductors. And up until recently, those were done in Finland, but this year they'll be fabricated in Canada. So it's a complete offering end to end, and we also do custom packaging for people who need help with that and so on. So I think it's quite a unique offering, and it's very powerful. And when I give that pitch in other countries, they all think it's a great idea. And so we've actually have customers in 22 countries around the world right now. We're working with Europe, obviously, Australia, New Zealand, Saudi Arabia, and we're talking to Brazil as well. We have some customers in Mexico already. So it really is a great lever to unlock semiconductors and make it very inexpensive for you to create prototypes. So I'm here today with Gary Hilson. Gary Hilson is a tech writer. I'm sure you have seen his name if you read any kind of technical articles. He's a freelance writer who's covered the scene for over 30 years. He began his career in the heydays of Nortel, and he's very well regarded for his coverage of the semi sector in the EE Times, which is a very widely read magazine in electrical engineering. And he's been a fierce advocate for their coverage of Canada, and it seems to be paying off now because we're getting more and more connection, or more and more publication in that thing. So I'll hand it over to Gary, and he will lead me astray.
All right. Well, it's great to be here, Gord, and it's certainly been very interesting. It's full circle for me because my career started in Ottawa, covering the heydays of Nortel and Mitel and telecom, and a lot of our heritage in semiconductors here in Canada is tied to that. We're going to touch on that. What we're here to talk about is this synergy between the defense industry and the semiconductor industry, and it's not new. It's ebbed and flowed, but if we go back to the post-war era, and it kind of speaks, the collaboration back then speaks to how we were able to get the costs down on some of these semiconductor technologies. So how did that post-war boom allow for the broader the semiconductor industry at large to become what it is today?
Yeah, well, I'll just put this up. There are a couple of ways that you can push R&D and product development forward, and one of them is war. And the defense industry unlocks the coffers, and a lot of things get invented and perfected and improved and so on. The other one is the space race. I really would prefer we did that a lot more, but both of them are happening right now. So yes, the first use of computers was to actually calculate ballistics, make up tables for ballistics equations, so you could drop your artillery shells onto your target more effectively. And so that was ENIAC, a tube-based computer back in the 40s. And if you've ever heard of Grace Hopper, she was eventually an admiral, but she was one of the operators of this first ENIAC machine. And they had to run around and replace tubes. It was all done with vacuum tubes at the time. They were very unreliable. They only lasted a few thousand hours each. So if you had thousands of them every hour, you could expect a tube to go. And she pulled out a tube that it was not functioning, and she looked underneath, and a moth had crawled into the works, and someone had plugged the tube down on top of the moth. And so she pulled it out, glued it into her notebook, and said, "I found a bug in the computer." So that's where we get the name for bugs now in computer software and so on. And I was around in the 70s with the IBM mainframes, and they were massive machines, and they would sit in one room, and you would have a dumb terminal in another room, or you would have a punch card reader and so on. That was a big progression, and they continued to move on. But that was really the switch from tubes to silicon. So the first, Intel processor was the 4004, which is the 4-bit microcomputer, and it started to get used in word processors and all sorts of odds and sods in the 80s and 90s. And today, of course, we have hundreds of billions of transistors on a single chip to go into servers and smartphones. And I talk to people about the growth in capacity, and I worry about it because a couple of years ago, the entire IC market around the world was $600 billion, but they were throwing $400 billion into new equipment and expansion. I thought, a market of $600 billion, if you're paying 2/3 of that in new equipment and capacity, that sounds like a bubble about to burst. But in fact, it's continued growing. And when I talk to the fabs about that, it's because there's the whole EV automotive market that is exploding. The smartphones continue to sell like crazy, and they get more and more capable. And the server market and AI, of course. So there's a whole, instead of having one kind of critical technology like compact discs or MP3 readers or whatever, we have a whole pile of simultaneous killer apps, if you like, that are really driving enormous amounts of semiconductor content. Sadly, we don't have any of that in Canada. We were well ahead of the curve years ago. And so in the 70s, 80s, and even into the 90s, we really were well ahead, and there were some amazing companies in Canada. So Mossade did a lot of dynamic memory DRAM design, and they got very good at it. And Dick Foss, legendary Dick Foss, he invented what's called the folded bit line patent, which was a huge performance improver for DRAMs. And so they got in the business of finding out who was using folded bit lines and asking them for royalties, shall we say, and which meant that they had to be able to decap chips, take them apart, and read them down, and figure out how they were being built, and so on. So they got into a whole reverse engineering kind of business, which is now Chipworks and Semiconductor Insights and folks like that in Ottawa. But at one point, they just controlled DRAMs everywhere, and they licensed their technology all over the world. And they did many generations of DRAM design. It was all Canadian, and just an amazing stuff. And at the same time, yeah. So at the same time, Mitel had fabrication. Nortel had a very advanced fabrication line. We really were well ahead of the curve on knowledge and capacity.
Right. So, I mean, I started out my career when Mossade was a big deal. Out of Ottawa, what we were calling Silicon Valley North. And,
Silicon Tundra.
Yes, Tundra. Newbridge, Mitel, Gandalf. Every taxi cab had a Gandalf modem back in the day. But, I mean, you bring it up to the smartphone, and that makes me think about today. Artemis 2 went up yesterday, and I watched that on my smartphone, 5 minutes out of Coburg on a Via Rail train on the CBC's YouTube channel. So that gives you a sense of where we've come, and I think about that makes me think about the miniaturization and the space program. And my favorite movie is Apollo 13. And there's a scene where Tom Hanks, before he goes up into space, he's giving a tour, and he boasts about how they have one computer that fits in one room. So maybe we can go back a little bit, though, because I think, miniaturization, the requirement for miniaturization from defense, I think that's a huge reason why we have what we have today is, the defense sector required smaller, and we're able to be the big customer to make that happen. So how important was that and continues to be important?
Yeah, there were big budgets for that, of course, right? Yeah, so if you're talking about equipment that a soldier needs to carry, it's got to be limited in order for them to be able to remain mobile and so on. And if you're talking about a jet plane that you want to be agile and have long range, and all of that stuff is super important that you manage to reduce size, weight, and power, just to make all of those things look better. And of course, anything you do, in defense applications, eventually has some sort of trickle down. Whether it's monitoring a soldier's health, it turns into a health event for average folks. Whether it's imaging, trying to find stuff. Important for defense, but also important if you're trying to find people who are lost, or identify objects in a forest fire, or just get all that background clutter erased. But it needs to be light and portable. And today, of course, everyone wants to mount everything on drones. So we're just talking to a company that does a radar system that can mount, is only about a kilo and can mount on a drone. And it's a phased array radar that can identify an object about 5 inches across from 4 kilometers away. So you'd be able to spot other drones in the air with your drone.
Yeah, and that
lots of interesting stuff, but it's the size and weight. And of course, if you can do that, you can do other things in the civilian kind of regime.
Yeah. I wonder how many appreciate, outside of us folks in the industry, or just general nerds, or sci-fi nerds, appreciate how much of the things we have today, the smartphones and the ability to post silly videos, has come out of defense, needing smaller, lighter things for defense applications, or the space race. I think one thing that's, defense really pushed, we need these smaller, lighter, and we need a volume of them. So that's, you speak about being able to do things in volume cheaply. To me, the defense industry was really a catalyst for this, kind of a post-war boom.
I'm kind of cranky about that because defense is a terrible customer. They want the supplier to do all sorts of work, to change it, to modify the software, to do more testing, to put them in the field. They want them to do all this work, and they don't pay for that up front. And then when they have the product they want, they order 1 million tomorrow, or 100,000 in a week, or something that you cannot possibly build, or that you can't finance. So it's a very difficult thing. And so our approach towards this, and I should talk a bit about fabric, but our approach really is that we want people to build things for civilian emergencies first. So get us a tag we can put on a first responder that measures their health while they're going in to fight a fire or whatever, and they can keep a track of whether their heart rate is too high, or their blood oxygen level is too low, or that kind of thing. And then, of course, that will translate directly to soldiers in the field. Mm-hmm. So we kind of want to go the other way, because those markets will be easier to sell to. We can sell to first responders, police, fire, search and rescue all over the world, and to other NATO nations. And that gets you a revenue stream, and it gets you up and running before defense comes along and places the big order. And for defense, it gives them hundreds or thousands of units in the field that are have been tested and proven. So they've got decent stats on what the reliability of the system is likely to be.
And similarly, drones are important for emergencies as well. To give a view of, say, a large wildfire, for example. I know drones are already being used for that, to get that bird's eye view, get photographs. And I know there's been some regulation changes here in Canada about drone use and how far they can fly. All this, that will hopefully lead to some innovation, and not to get too far off the emergency preparedness that because I think certainly we live in a climate where people are worried about climate emergencies and storms. So I think that's a great place to start because people see the benefit. But even broader industries, like mining, that health monitoring is good for miners, and the drones are good for maybe seeing what a field looks like, so you don't have to drive a tractor out. So the emergency response, great way.
Farmers don't have money. I have a farm. I have no money. Yeah, that triggers a couple of ideas. I see some really interesting stuff going on in the chat, and someone talking about not having a fab in Canada and so on. Nvidia doesn't have a fab, and their market cap is what, $2 trillion right now. So we could do more of that. And we've had some unicorns. Novotel, BlackBerry, Nortel at the time was up to $30 billion in sales, right? So we can build those companies here in Canada. We seem to have a problem keeping them going forever. But we have a really intriguing project now. If you've heard of the Sudbury Neutrino Observatory, the SNO Lab, it's a kilometer or two underground in Sudbury in an old mine, and it captures neutrinos coming off the sun. And it's a very rare event, and so they have a sphere that's filled with fluid, and they capture neutrinos. They react with the fluid, and they can capture photons that come off that. But they want to build a new one that's and instead of a meter across, it's 3 meters across. So they're going to make these single photon avalanche diodes, millions and millions of them, to coat the inside of this sphere and capture many more signals and so on. But those SPADs can be used for other things as well. And you can imagine they're going to be built at Teledyne in Canada, in Bromont, and they're going to be packaged at IBM in Bromont in Quebec, and almost all of the operation will be done there. So the beauty of that is we can then tailor the SPADs to do different things. So imagine you fire a laser a few kilometers away into a cloud, and you can tell whether the cloud is wood smoke or water vapor or radioactive dust by seeing what kind of photons the SPAD picks up as the laser interacts with the cloud. So that would be a brilliant spin-off of a big science project, which is going to cost about $300 million. But we can take that same technology, modify it, and then use it for a variety of other things. So there's some great Canadian, seeds that can be spun out into really fascinating technology.
That really speaks to the idea that we have developed, very specific capabilities in Canada. Despite not having the big fab, we do have these really robust capabilities in some technologies that will be important for defense applications. And we can go back to the 70s, the Communications Research Center, which still exists today. It's certainly evolved, but that speaks to all that telecom heritage, the Nortels, all the Newbridge spin-offs. And I remember, yes, early in my career, I covered several, Newbridge spin-offs in the mid to late 90s. And then, of course, we hit a bump in the early 2000s. There was the dot-com bubble, which not specifically tied to semiconductors, but we had that Nortel, that loss of Nortel, but that heritage hasn't gone. And that we speak about seeds. So we sort of had this period where I guess we could say the music stopped for a bit, and there was a lull. But all that heritage, that know-how that came out of Nortel is really what's feeding some of the companies today in compound semiconductors, photonics, and the packaging. So maybe speak to how important that is where we are today.
Yeah, you're leading into to fabric. So we went to the government a few years ago and we said, look, we have these factories in Canada. They don't do highly advanced transistors, no, but there are some areas where we have some real expertise, and these are areas that are exotic, that require brain power. They're high growth, they're high margin, but they don't require massive capital investment, and so the tens of billions that we require otherwise. And so we selected compound semiconductors because we have the old Nortel equipment was sold for pennies on the dollar to the National Research Council, and they created something called the Canada's Photonic Fabrication Center. And they have a number of large customers. They're doing diode lasers, and we are developing a process to do photonics in compound semis, in indium phosphide and gallium nitride with them. There are MEMS, or micro electromechanical sensors. So these are mechanical sensors built with semiconductor technology, and they're used in your tire pressure monitors, in gas airbag detectors, accelerometers, and that sort of thing. There are probably half a dozen of them in your phone to do various things. If you have any of those science apps, they'll show you. There'll be an accelerometer in there. There'll be an inclinometer and all that kind of stuff. So we can build those MEMS, and in fact, Teledyne, with their factories in Bromont, Quebec, and Edmonton, Alberta, are the world's largest open foundry that takes on customers for MEMS devices. So they have hundreds of processes. They do all sorts of different kinds of chips. But the beauty of it is you can only get so small in a mechanical device before it breaks. And so they don't have to scale down to angstroms, to nanometers. In that factory, they continue to use the same kind of equipment they had before, and it's very clever rearrangements of layers and deposition and etching and so on that makes the various types of products. And photonics is the same. Photons don't change in size, so there's only so small you can go with a waveguide or a modulator or a ring resonator, and so the equipment doesn't go screaming off down this this curve of higher expenditure. So your equipment can be good for 10 years as opposed to 18 months. It's a really hot area right now. If you know Ranovis in Canada, Hamid is the CEO is very committed to staying in Canada and trying to do as much as he possibly can in terms of packaging and fabrication and everything else here. And super, and they just had a phenomenal growth, because in a data center, if you're watching Netflix, just downloading videos and so on, only about 10% of the power is used by transferring information back and forth between computers in the data center. If you're doing AI, about 50% of the power is in transferring from one rack to the next rack or within the same data center. So what they do at Ranovis is they convert that electrical signal to an optical signal, and they send it down a fiber. So you can send many, many more signals with much less routing, and there's almost no power lost in the fiber. So it's an extremely efficient approach, and it's been picked up by all of the big players who are doing data centers now to try and reduce their power needs. And that's all Canadian stuff, right? Just it's an amazing success story, Ranovis. And in photonics, of course, a lot of that stuff was done at Nortel in the day. They invested a ton into fiber optics and modulators and all of that silicon photonic stuff. So Optonique, just in Quebec alone, has a census of about 220 companies in photonics and optics. That too has been a big success story. That all those companies are still around, and they were founded by ex-Nortel engineers for the most part, who had all these skills.
There's a couple of threads I want to follow from this, and it's the photonics thread, but also the compound semiconductors. So, I mean, the photonics, one of the things that has come up with what I've been writing about specifically for EE Times is photonics and optical technologies, are really critical for all these AI data centers, for one thing, as you say, getting, moving data around efficiently, low power, because these data centers are just so power hungry, and moving data within the data center is still a big part of it, no matter how powerful the GPUs are or the high bandwidth memory. But photonics also plays an enabling role in quantum. So could you speak a little bit to that? Because I want to bring this all back to defense, because that's why we're here. Because there's some really there are some real world quantum technologies that we outside of quantum computing, which still has some work to do, but quantum sensors. So I mean, we talk about photonics, how it enables quantum, and maybe we can touch a little bit about quantum sensors and what they're able to do today that have some defense and emergency preparedness applications.
Oh boy, can of worms. Someone asked me on a panel one time, what is the use of quantum technology? And I said, well, anything any research you do can be published immediately, and anytime you want to raise money, quantum is the word to use. But Canada invested early in quantum, and we had the quantum institutes, and we did a lot of work and a lot of training early on. And then, suddenly the U.S. and China started throwing money at it, so that their per capita investment was much higher than ours. But we still have an amazing number of startups that gravitated and respond here in Canada. So we are well above our punching well above our weight in quantum in general. And there are a few companies. One is SB Quantum that are doing nitrogen vacancies in diamond that can be used to do magnetometers. So if you can do magnetic sensing, you can kind of fly in a plane or put it in a satellite, and you can roll over the Earth, and you can determine where there are magnetic anomalies and changes and so on. And so it allows you to determine where you are without using GPS. So if there's GPS denial, if someone's shooting down your satellites or blocking them or spoofing your GPS, you can use this as a secondary measure for navigating. But also you can determine if there are deposits of heavy ores under the ground. So for mining, it's great for spotting reasonable sites to dig and so on. Really amazing stuff. And now people are actually putting quantum sensors into human cells, and they can determine magnetic field variations and things inside a human cell. There are just an amazing number of applications for that. And on the computing side, we have been very lucky that ICED and Canada are very keen to see companies adopt. And so we have our own quantum computing group, core group, and they take a customer's problem, they massage it, they change the code from Python or C to code that can run on the quantum computer. They run it, and then they hand back the results. And we've done over 30 projects. And we just opened our quantum sandbox, which is 100% funded by ICED, by the Fabric program. And companies can submit and get a 6 to 12 month program to test the waters and see what quantum can do for them. And what's starting to show up is that there are kinds of problems, especially in health science, where you're trying to determine which group of molecules will best bond to a strand of DNA and so on. And you might have 100,000 candidates, and quantum might identify the 10,000 that are more likely for you. So because they're still noisy and not exactly decisive, what we have to do is run the same program maybe 10,000 times or 2,000 times, and we look at the preponderance of answers that it gave. And it may have given this answer 27% of the time, and this answer 13%, and the other times it was thrown off by some sort of perturbation, either temperature or an electronic signal or something. But looking at those answers, you can kind of hone down on what answer was it trying to get to, and where are we headed. So it's it's great for handling huge data sets, and it does give you these tendencies that you can then feed back into high performance computing. So I think there are benefits starting to show up in quantum computing. There are certainly benefits in quantum sensing, and quantum communications. Now there's a group called KIRQ, KIRQ, who have a quantum-enabled network between Montreal, Sherbrooke, and Quebec City. So you can actually test out equipment and see if you can hack their system and try out real quantum computing or quantum communication systems. So all of that stuff is moving ahead slowly. It's kind of got past the hype cycle, and it's into the valley of disillusionment or whatever, but crawling its way out and starting to show up real benefits. And you just saw Xanadu with their photonic computer just go public. They're an amazing success story right in Toronto.
Mm-hmm.
There's an awful lot of good stuff going on here.
That kind of speaks to, because we've talked a lot about the Nortel heritage, the telecom heritage, which is very Ottawa based, but the capabilities we have spread across the country in various pockets. There's quite a bit the Bromont area, and on the west coast there's a lot of quantum activity as well. So it's not just focused in Ottawa, which had that telecom heritage. And I want to circle back, as maybe it's not as sexy a technology as quantum, but compound semiconductors. We spoke about compound semiconductors, and I'm mindful of maybe the audience that maybe not everyone understands what a compound semiconductor is versus maybe the conventional idea they have of, say, silicon. So maybe you can speak to, what it is and what's different about them, and what maybe why are they, what kinds of applications are they useful for in a defense environment?
Yeah, so the silicon is a natural semiconductor in that there are a variety of ways you can make it either conduct or not conduct. It can become an insulator and block the passage of current, or it can become a conductor and allow current to flow. So you do that by polluting it chemically with different kinds of what we call dopants. You can do it by applying temperature, or you can do it by applying an electric field, which is how transistors are all functioning. But silicon is in column 4 of the table of the elements, but there are compounds in the rows 3 or columns 3 and 5, like gallium and nitride, or gallium and arsenic, or indium and phosphorus. And so they can be combined together to actually make a semiconductor. And the difference with most of the compound semiconductors is electrons tend to travel a bit faster in them, so they can do higher speeds. They quite often have a larger, what's called the band gap, so that they can be used at higher voltages. And so this is why you get 600, 800, 1,000 volt gallium nitride transistors, but not in silicon. And they can withstand the higher temperatures typically. And also many of them are inherently rad hard, they're radiation hardened. So you can put a GaN transistor, a gallium nitride transistor, into space, and it won't degrade over time anywhere near as much as a silicon transistor would. So there are all those kind of benefits. They're used a lot for power in radars and in lidars and things like that, where you want to drive a high voltage signal, 30 or 40 volts at reasonable currents. There's a lot of unique applications. They are more complex or difficult to fabricate. There are not so many suppliers of the raw materials as there are of silicon, of course. Obviously, it's not as big a market yet. But Daniel has just also pointed out that silicon can't generate light, can't generate lasers, whereas compound semis can, because of the band gap difference. So you can create a light, you can put it into a fiber optic, and then you can detect it at the far end, all in a compound semiconductor device, where you can't necessarily do that in silicon.
Right. Given these challenges, though, are the defense requirements, something that can make the case, as in the past, whereas if there's a demand for that rad hard or these characteristics, where it's there, that will push past, the barriers, the challenge to say, hey, it's worth doing, and lead to driving down the cost of doing it, because over time.
Yeah, well, certainly you can't get the performance out of silicon, period, right? So if someone's got a really demanding aerospace kind of application or whatever, then you're going to go to GaN or INP, indium phosphide or gallium nitride, to do that function. And there are not a ton of fabrication facilities around the world, especially in indium phosphide. There are 3 or 4 in China, which are a little less accessible these days, and then there's a couple in Europe. So our CPFC in Canada is a real jewel, and it has very high performance devices. They're well respected, and they have some very big clients right now. So there is a discussion. They've just done a $90 million expansion, and there's some talk about building another commercial fab. It'll be about $500 million somewhere in Canada, probably around the Ottawa region, to be close to the CPFC. So there's a lot of, the pitch was made by a whole group of companies in Ottawa to do that. So we're looking at, $500 million to $1 billion sort of investments to get these foundries up and running. And photonics, of course, another great place. Back in the 70s and 80s, you could actually build transistors in a university lab. But as time went on, they couldn't keep up with the equipment costs and so on. And then there are 44, 45 nanofabs across Canada. In fact, maybe someone can put in the chat the link to our map of nanofabs across Canada. There are 47 of them, I think, and we're just about to add the NRC labs and a couple and other folks like the C2MI and INO, or Lucia, as it's called now. And so there's lots of capacity, but they can't do transistors anymore. But they can do these photonic devices. They can do MEMS, and some of them can do compound semis for a research sort of environment. But if you can get your product up and running in those areas, then you can transfer it to larger foundries like Teledyne or like the CPFC. So there's some great opportunities. There you are. It's just popped into the chat. This is the Canadian Micro Nanotech Labs. And at CMC, of course, we pride ourselves on being good at sharing internationally. We are getting a ton of love from both Europe and Asia right now. People coming to us and asking to collaborate, and so we are part of what is called a Global Nano Lab organization, and it's Australia, Japan, Canada, the U.S., and Europe, and we're adding new partners constantly. So this is just the Canadian micro piece of that, and it's accessible to all the members. So you can find if there's a specific technology you need to do a specific product, whether it be defense or anything else, we can find those folks and get in touch with them. So it's a very funny kind of the middle powers, as it were, right? I love the Carney talked about middle powers and so on, but we are all banding together at the research level and trying to share expertise and the capability. So the UK is also very hot on this, and so they just announced the Canute network on March 18th in Ottawa, and it's UK and Canadian researchers collaborating on various projects. So we already have some collaborations on graphene and silicon carbide and a few other things that that CMC is sort of assisting with and getting in the middle of. But we're hopeful that we can get more of these collaborations going.
Yeah, and I seem to recall having a conversation with you in the last year for one of my EE Times articles on compound semiconductors that there's a lot of activity in Wales.
Yes.
They need some help to scale up. They've got some good research capabilities, but they could use a little helping hand to push things forward, and that's something that we have.
Well, the really interesting thing about them is they just produce wafers with a specific stack of materials on them, and they have a few standard recipes and so on. So if a customer wants something custom for their purposes, they won't take them, and so the CPFC can pick those up. So it would be a great source of customers for the CPFC to take the non-standard stuff and then develop custom recipes for these folks. So it's a good partner, yeah, and they're very, very keen on working with us.
My sense is, and again, this includes some of our conversations over the last couple of years when I've come to you to sort of understand where we're at on certain areas of semiconductors, so I can write about Canada's capabilities. Despite we've been quietly bubbling along in the post-Nortel era on many fronts, again, where we have these capabilities, compound semiconductors, photonics, and then the quantum, the consensus I've gotten from people talking in Canada's quantum community is, we are keeping pace, with the rest of the world. We're putting the investments in. So now that we have a government that has really explicitly said, we are putting funding into defense. We started with the need to meet our NATO commitments, which it looks like we've hit. But the strategy that recently came out. How do you feel? Where can these capabilities intersect? Whether it's compound semiconductors from photonics and quantum and MEMS. What are the opportunities here? Now, as this is a defense is something we're really explicitly talking about again.
Yeah, the big ticket items, it's hard to kind of see where the semiconductors fit, but they are full of them. I was talking to someone who was saying, we can build a destroyer in Halifax at the Irving shipyards, but for the same money, we could get 3 from Korea. They're much better at building destroyer hulls, but we can load it up with Canadian technology for sensors, radar, LiDAR, all of that kind of stuff. So that would be a great place for us to fit. Now, I think we're still going to end up building our own destroyers, even if they are more expensive, because we want to maintain that capability. But it's an interesting thought. So we really, if we're talking about drones, lots of people are building very capable drones around the world, but we could do very unique sensor packages. And so those sensors involve things like there are infrared sensors from the INO with the process technology has been transferred to Teledyne, and we can make an infrared camera on a chip, incredibly sensitive and uncooled. It doesn't require any special hardware to run. So I think putting sensors onto drones is a great place for Canada to fit, and a lot of these compound semis are very useful for that.
It's part of a stack. We get into the stack.
That's it.
And it's a proving ground, but there's opportunities internationally, where we can, I guess, put a stake in the ground on some of these things.
Yes. And, I really do want there's academic research, which is all very well. And then eventually, you hope that it gets some legs, and either they spin out a company or someone comes along who wants it. But really, where I think the best way to spend our money, if you like, is the way we do it in Fabric is we make sure that they can actually they're big enough, they've got a product perhaps, and they want to do a next gen. And so they're big enough, they have enough revenue to actually afford the development, and then we subsidize them to about the 30 to 40% level. And they provide us with their expenses for the last quarter, and we cut them a check to help them defray costs and so on. So I think a lot of this, whether it's civil emergencies or human health or defense stuff coming along, if we can help them to lighten the load on the development and go a little faster, we can hook them up into our network. We even have technical staff on within CMC who can help in making the decision as to what technology they should use and which will be best for them. And we can speed up those developments. So we've been doing that with Fabric, and in fact, what we'll do is we will have a call out for defense tech within Fabric, probably in the next couple of quarters. So we'll see how that goes. But really, we want to accelerate a company that's building and developing, and we want to get them to a product. So we want to get them from fab to field, where they've got hundreds or thousands of pieces in the field, and they actually get to gather real data on them. So that has been our approach, that we're trying to accelerate companies through the valley of death sort of thing, from first prototypes, first products to a second gen product or a third gen product that looks even better. Government is a bit, which we say, careful, because they don't want us funding, multinationals with tons of cash. They don't want us funding companies that don't necessarily need the cash. So we have to be careful about identifying those opportunities. But that is all done by a network of experts externally, and they make the recommendations as to which projects we should take on. So our first expressions of interest. We had 138 EOIs come in for more than the entire 5-year budget. So we had to turn it back. In the end, of the ones we asked to submit proposals, about 1 in 3 was funded. So we had 20 projects launched initially. We have another 12 we're about to launch now, where the success rate was about 1 in 2. And we'll have more competitions, and for some smaller amounts and smaller projects, just so we can keep things rolling with as many companies as possible. And there'll be we have a proposal for a dual use and emergency technologies, which will be larger than Fabric, and I hope can spur a lot of these in civilian emergency, first responder, defense kind of things.
And I know some of the first early rounds of ultimate recipients of these of the Fabric program. You mentioned Ranovis, I believe, is one of them in the photonics area, and a lot of there's some healthy photonics representation, and some IoT as well. And bringing back to defense, both those areas are very lots of applications for defense. Because Fabric was already happening, before we've amped up this, these defense discussions. but given the historical intersection of defense and semiconductor technologies, and some of the things, we could go on and on, and defense, the miniaturization is why we have the pacemaker. That's a pretty mature, pretty mature technology. So that we go back to that miniaturization, but it looks to me that already there's some end use industry focuses, around oceans and mining, and those, again, the rad hard, or just in stream environments. Anything that has to be work in an extreme environment, and that could be an emergency because you've got,
Smoke,
hurricanes,
dust.
flooding,
Yeah,
fire.
yeah. So yeah, so obviously Arctic environments are one of those, and so we'd like to have a competition to look at how do we put sensor networks out in Arctic environments and continue to have them draw energy and store energy and so on. But I was in Dubai in January, fortunately, and they have a center there for robotics, and their big constraint is how do we get a robot to work if there's a dust all in the air, if there's sand and a sandstorm and that kind of thing. And that was really intriguing to me because it could be sand, it could be rain, it could be snow, it could be whatever. What is going to impair the mechanical movement of this device?
Mm-hmm, mm-hmm. And even under, and then underwater applications, and the very discrete applications, might be developed for a very specific thing, but they can be transposed over because they can handle extreme cold or extreme heat, and then speaking to that spillover, because this is what has happened, historically, because we decided to put people in space a very long time ago. We ended up with a lot of technologies that we take for granted, but there's an opportunity for more spillover for something specifically designed for defense or emergency preparedness. And I know I wrote a piece recently about drones, and there's a Canadian company that is specifically focused on drones doing tasks like repair on a remote oil rig, for example. And they got to go and they're going to weld anywhere where they see they need to get welded. So that miniaturization, again, that lightweight, we come back to that. I'm mindful of time. We've got about 12 minutes to the top of the hour, and I'm wondering if you saw any questions come in on the chat that you'd like to answer or bring up for discussion.
Well, there was some talk about Canada having a semiconductor fab and so on. So I was listening into some folks, and we were, the U.S. launched CHIPS Act, $52 billion to accelerate the semiconductor fab there, with a real emphasis on the advanced, blazing edge fabs. And so people were talking about, what if we did a $5 billion pro rata for Canada? And they were talking about doing a trailing edge fab at 65, 90 nanometer, that kind of thing. But the trouble with that is, if you built the fab, you would need to have process technology. You need to have customers to fill it. And you're going to be competing with fabs that are fabrication facilities, as I use the word fabs, everyone does. They're going to be competing with facilities that are totally paid off. Their capital was paid off years ago, so they only have variable expense. So it'll be a money pit forever. And it'll take you years to fill it with customer designs and processes and all of that sort of stuff. So I didn't think that was a great idea. So I wrote a piece on how you would optimize the ecosystem by building 5 $1 billion fabs and targeting some specific applications like compound semis, like photonics, like MEMS, and advanced packaging. So imagine you put in Southern Ontario, in the auto kind of zone, you put an advanced packaging facility where you could develop high voltage packaging and high voltage modules. And the module with the batteries could potentially have a thermal sensor, a current sensor, some AI that's determining the health of the battery and so on. And it could shut the battery off using, again, a compound semiconductor switch. You could disconnect that battery if it's going bad from the pack so it doesn't start a fire. And that kind of technology, once you've got it going for that application, there are many, many board shops, printed circuit board assemblers in Southern Ontario, and they often get confused with semiconductors because the North American Industry Classification System, NAICS code, includes everything electronic under the term semiconductor. So all electronic assembly, all the printed circuit boards are all included, and that's just embarrassing. So they talk about, billions of dollars of semi. There's probably less than $1 billion worth of real semiconductor fabrication in Canada, to be honest. I'd love to see that grow into the tens of billions, but it's not there just now. And our intent is to try and and grow it. But you can imagine a packaging facility could then take on contract R&D, and that would help it to cover its own OpEx. And it would be a resource for the automotive sector, but also for all of those printed circuit board shops to give them new modules, new packaging techniques, new packaging technologies, using compound semis, whatever, to make a more interesting product. And so we should post that piece somewhere on our webpage under the blog or something. I've got a whole lot of sort of odds and sods where I had an opinion. And wrote it up. So I'd be happy to share that with anyone who wants it.
Yeah, and you mentioned automotive, and that's a whole other discussion because defense and automotive have a lot. Again, it's those harsh environments, that extreme environments, because cars have so many systems in them and chips, and you might want to have something really close to a hot engine. And you also want to have something that'll survive a Winnipeg winter and start up. Because we want those systems, we expect those car systems to start up immediately. And I've written a lot about certain memories that have that instant on, because people expect the fancy dashboards are all got computer chips in them.
Someone asking about DRAM facilities. DRAM, Mossade is still around. I don't know exactly what they're doing. I haven't talked to them in a while. Someone else is looking for a meta lens for a time of flight sensor. There is a company called Meta Materials, I think, out in Vancouver. I'll hook you up, Rocky. And there are certainly some fabs, some labs across Canada that do that kind of stuff. Any questions from folks? Feel free to put them in the chat. I've had some fun talking about the old days. The map you see there was done, I think, originally by Yole. They're a European market research firm, and so they kind of created all the clusters across Canada. So BC has a lot of design shops. Vancouver is well known for that. We have quite a lot. I would say about 10,000 IC designers in Canada, because IBM, Dell, Ciena, they all open offices in Canada. Well, I shouldn't count Ciena because they started in Canada, but they find Canadian engineers highly skilled. I like to think that's because they got trained with CMC tools. They pay in Canadian dollars. They don't have to pay for healthcare, and so it's when they look at the ROI, the return on investment is just fantastic for design centers in Canada. So they tend to grow faster than their centers down in the U.S. So, well, yes, okay, yeah.
I was going to suggest, at the time we have left, maybe speak to the talent, what we're, in terms of the types of talent we have, and how we're, the training aspect, because that's important as well.
Yeah, so we provide the computer-aided design tools to about, it's Mossade is the DRAM company, MOSAID. So we train about 12,000 people a year annually, and then about 2,000 of them graduate. They're going through master's and PhD. We are always trying to increase those numbers, but and about 400 a year do a unique prototype design that we actually end up fabricating for them. So they come out and they've done a design, build, test cycle. They've made their mistakes on our dime, and they go to industry. And we had a third party look at our graduates, if you like, 900 of them. And they were 6 to 18 months faster time to productivity when they went to industry. They were 25% more likely to be in senior management within 10 years. And they stayed with their first company for 1 to 2 years longer than other folks because they were a better fit and better appreciated. So we're very proud of that. And the 2,000 that graduate every year, about 1,000 go directly to Canadian industry. About a quarter either continue studies or go to a research institution like the NRC, and another quarter go to their home country. But of the 500 who go to their home country, we have 1,500 who stay, and of the 2,000, 1,400 of those were foreign students. So we're gaining about 800, 900 brains a year from foreign students who come here, do their studies, and then decide to stay on and go to Canadian industry. So it's a really wonderful result, I think, for Canada. And unfortunately, the visa problems we've had in the last few years have made it a lot harder.
Tie this into some of the fabric projects as well, because conceivably, to get, you're funding things that just need to get through that Death Valley. And how often is it we got to develop some skills within the company if we're going to scale up this product and the company? So how does fabric help with, just maybe nurturing, the right talent to solve problems that you'll get that capability, so even after that specific product, that's going to stay with the company and help them solve even more problems in the next version.
Yeah, certainly a fabric. A portion of the funding is to subsidize the academic access. So we charge a small amount. It's about 30% of the actual cost of the CAD tools for researchers in academia, and then we subsidize their fabrication about 50% as well. So it's a relatively cheap service. It's still difficult for some of them to to find the money, given the current situation in academia, but I hope that will straighten out soon. And we're asking, and the other problem is they go into more and more complex processes and smaller line widths and so on. So those processes get more and more expensive. So that too is a complaint, is that we subsidize 50%, but if it costs $40,000 to do a prototype, they can't find the 20 that they need to put in. So we're asking for more subsidy in future projects with the Canadian government, and we're also asking for help from the provincial governments. So it may be that your province will have better subsidies than another one if they come forth with those funds.
And we're kind of run out of time, but I'm thinking some defense projects or defense applications can add some certification challenges as well. It's not just about the technology, but really making sure that technology makes a very specific set of requirements. And that those are other industries have it as well. The automotive has some reliability demands, and medical technology has, if you're going to put something in a person's body, that creates, it's not just the technology itself, it's whether it can do it in defense or in automotive so that can add, I guess, some challenges on the skills.
And again, the reason why I'm suggesting that we go after first responders and civilian emergencies first, because the barrier is a little lower, and it gives you time to go through all the certification they need you to go to. And I understand there's a new spec that's going to be enforced near the end of the year for the U.S. For anything to do with the military, called CMMC, that will force you to jump through all sorts of hoops in order to get your product certified, and your company is certified to produce it. So there's going to be a high barrier there. It'll take you years to get through it. So let's get you to a product that you can sell and keep moving on.
So there's a lot going on fabric and CMC front and defense. It's a kind of it seems like a perfect storm of good stuff. And so how can people keep tabs on all of this and get in the loop?
Sign up for the newsletter. If you go to cmc.ca, you'll see a newsletter button. If you subscribe to that, you'll get a monthly report on what's happening, what international stuff we're doing. I see someone was asking about international collaborations, and we do have a lot of those. And many countries are coming to us. The CMC sort of recognized as the semiconductor font of wisdom in Canada, and so they come to us and they want to see if they can do something collaborative. So we're looking at doing a 1.6 terabit per second optical transceiver with ITRI, the Taiwan Research Institute. We were looking. Fraunhofer has been asking us to help them with quantum. It's been a very exciting time. Our poor neighbors to the south are kind of getting neglected, but anyway.
We have covered a lot of ground and touched on a lot of things, and I think the hope is on a regular basis we'll be narrowing in and on some of these things that we've spoken about, quantum, for example, and photonics, but also the continued attention on defense and dual use technologies.
Top of the hour. Thank you, everyone, and I will look through the meeting chat and get back to you with answers if we haven't talked about it. Thank you so much.
Thanks, everyone.